Hello everyone and welcome back. Now, for the past two lectures, we've been talking about dynamic mode decomposition. Now, what we've seen with dynamic mode decomposition is that it is a powerful method that has a similar objective to proper orthogonal mode decomposition, but with the additional property that the time dynamics become linear. And what I mean by become linear, I mean they're really sort of governed by linear dynamical systems. So the solutions are only sines and cosines or exponentials. Nothing more complicated than that. Now, I would like to continue this discussion of dynamic mode decomposition, but I would like to approach it from a different side, and that is the perspective of time delay embeddings. Now, before I get into time delay embeddings, I want to motivate the problem with a really simple example. Okay? Here's what I want to do. Imagine I give you the following signal. I'm going to think of one of the simplest possible signals one could have, sine of t. Okay? And what I'd like to do with this signal is, first of all, I'm going to subsample it at discrete time points. So imagine I give you data from this signal. I'll call it xn. The nth data point is going to be x of n times h. H is going to be a discrete time step. It's the sampling rate. You know, it's how quickly I can sample this thing. N is just how far into the signal I've gotten. Okay, so of course this is just sine of nh. H is of course going to be assumed to be positive, but if you look at this, it seems very simple. However, if we wanted to apply dynamic mode decomposition to this, you'll notice that this is, a one-dimensional signal. It's a real valued signal, right? So if you use the language from dynamic mode decomposition from a few lectures ago, you remember that in this case, m, the dimension of the space, is equal to 1. And the DMD matrix is going to be a 1-by-1 matrix. It's going to be a real value. So DMD is going to try and do this for you. DMD is going to try and fit a linear dynamical system that looks like this. And it's saying if you want to advance in time along your signal, all you need to do is multiply by a real number a. Now, you can probably see what the issue is here, because the general solution of this thing is just exponentiating a, right? Remember, a is a real number, so I can't get any oscillations in here, whereas my original signal was oscillatory, right? It's just a sine curve. It repeats over and over. However, DMD is going to immediately fail. And of course, I can come up with way more complicated examples than this, but if DMD is going to fail on this, I've already got a huge problem, because this is, one of the simplest signals to predict in, all of mathematics, engineering, signal processing, whatever. So the question is, how can we augment our DMD strategy in such a way that we can account for at least this basic signal? And actually, the way that we're going to do this is by looking at delay coordinate embeddings, okay? And the first method that we're going to look at is we're going to say, instead of just fitting a single real number here, what I could do is I could look for the next time step as, say, some real number times the current time step, plus another real number times the time step before that. And you could go all the way back in time to some finite, I'm going to call it tau, which is going to be my delay here, xn minus tau. So basically what this is doing is it's taking not only information from the previous time to go forward, as DMD would have done, but it's saying, give me a little bit of the backwards dynamics here so that I can use them all to push myself forward. Now, it turns out that this idea is very old in the statistics community. This is sometimes called an autoregressive moving average, an ARMA model. Okay, so this is not a new idea, except for maybe in the context of dynamical systems. Now, another way that you can see this is it's actually a variant of DMD where I have my big data matrices. So if you remember how I put DMD together, essentially what I'm doing is I'm inflating the dimension of the dynamics here to account for the delayed coordinates. So for example, if I took my original signal up here, if I did x1, x2, all the way down to x tau, so some, my delay coordinate, that is my entire first data point, not just x1 anymore. It's including time history or future time steps all the way up to tau. And then I did in the next column, x2, x3, all the way up to x tau plus 1. And along every single row and column here, I'm advancing by some amount of time. So let's say this goes up to x to the n minus tau minus 1. Capital N will be how many time points we have. xn minus tau minus 2. And then all the way up to x capital N. Okay? So in this case, just like the original DMD setup, you have time going across the columns, but now your sort of space, quote unquote, is all a bunch of history of the system as well in time. And of course, if you want to throw DMD at this, that means that you are going to have the next time coordinate, which again will be captured in a huge matrix, and it's just going to be this shift here. Sorry, this goes up to n minus 1, pardon me. And then this would be x2, x3, all the way forward to x tau plus 1. And that comes from the fact that you want this column right here, its next advanced in time is this column right here. x1 goes to x2, x2 goes to x3, x tau goes to x tau plus 1. And at the risk of me writing a lot here and maybe boring you, here you're going to have x tau, and then you're going to have x of n minus tau, x of n minus tau plus 1, and so on and so forth, right? So that each column is pairwise mapped into each column of y here. And if you try to apply DMD now to these two delay matrices, which we call a Hankel matrix. Now, a Hankel matrix is this big matrix of delays, this big square matrix. Of course, tau is a hyperparameter now. So if I use these matrices right here and apply a DMD algorithm, just your sort of standard DMD algorithm, what you would effectively be looking for is a DMD matrix that should mimic this ARMA model, which would be something like this. 0, 1, 0, and then zeros all the way across. And all that's doing is pushing you forward 1 unit in time. And then 0, 0, 1, zeros all the way across. And you would do this until the second last row. So let's do this, where you have a 1. So all this is doing is pushing each time step forward until you get to the very last time step, where you would have a tau minus 1, a tau minus 2, all the way over to a0. And that last line is just recreating this piece right here, okay? That's all that it's trying to do. So what you see here is these time delay coordinates, these Hankel matrices, result in something very similar to what we saw with physics-informed dynamic mode decomposition. We have a specific structure that we are trying to impose on the DMD matrix. In particular, there's only a small number of coefficients for the DMD matrix that need to be found, the ones that represent this ARMA model. Everything else is zeros or ones. In fact, there's so many zeros that I would classify this matrix as being a sparse matrix. This is another numerical advantage of using these time delay coordinates. Let me show you a specific example. Let's go back to where we started with my sine curve, okay? So in this case, I've got xn is equal to sine of n times h. Now, I want to just write something here for you. I want you to notice that in complex coordinates, it looks like this. E to the I n h minus e to the minus I n h. So what I've done here is going to be important for the general theory that I'm going to outline in a second here. But what I want you to really just notice is that the complex Fourier series of this signal really only contains two terms, okay? The complex conjugates of each other, right? But they make up the original sine signal. And I'm going to really only talk about the complex Fourier series when I talk about the theory here. But first of all, let's create an ARMA model that uses only one time delay. Let's see if we can do this, if we can reconstruct this signal just using one time delay. So that would mean that I want xn plus 1, so that's sine of n plus 1 times h is equal to a naught times sine of n times h, and then plus a1 sine of n minus 1 times h. And again, if you just pay attention to what I have here, this is xn plus 1, this is xn, and this is xn minus 1. All right, so it's just an ARMA model. There's only two terms to be obtained here. Actually, I'm going to leave this as a fun little exercise for you to work out on your own. Really, all it is using some trig identities. And what you'll find is that this is explicitly solvable. You're going to find a naught is equal to 2 times cos of h. And you're going to find that a1 is equal to minus 1. And so what that means is that using only one time delay, right, a1 here, I can fully reconstruct this signal using DMD. Okay? Also, if I put it in terms of this matrix right here, I could find a DMD matrix that looks like this. I'm going to call it ADMD for the DMD matrix. It goes 0, 1, and then minus 1 cos of h. 2 cos of h. The important thing to notice here is it doesn't matter the sampling rate. I can always make this work for any value of h, and I can always reconstruct this signal using a single time delay. Okay, so let's go back to the theory. Can this always be done? Well, it turns out that you can prove in very similar ways that I've done here that if your signal is composed of a finite number of complex Fourier components, then you can always reconstruct it using a delay model perfectly using 1 minus the number of non-zero Fourier components you have. So let's take a look at this example. Here I have a sine function, which I said is 2 Fourier components in the complex Fourier series. So 2 minus 1, that's 1. That is only one delay needed to reconstruct this signal. So this is a very, very powerful method on what are called band-limited signals. These are signals in which only a finite number of Fourier modes are activated whenever you are whenever you look at their Fourier spectrum. Now, just while we're on the topic, before we sort of cross into some numerics here, I want to talk a little bit about an alternative method here. And this goes back to my Hankel matrix, okay? So here, remember, we're initiating the DMD method using these Hankel matrices. There's another way of using these to get some interesting information and apply DMD as well. And this comes from a rank reduction method. So first thing that we're going to do is apply the SVD. So remember, we're going to take our Hankel matrix X. This is all of our delayed data organized for us. We are going to take the SVD of this thing. And then what we'll do is we will identify a target rank. So for, let's say, r greater than or equal to 1, let's consider this matrix. Remember, UR, we talked about this for the reduced SVD. Now, this thing is really going to be the first R columns of the orthogonal matrix U. And what I'm going to do is I'm going to look at, instead of the whole Hankel matrix, I'm going to look at a projection onto just the first R columns of U. And because I did that for my matrix X, I'm also going to do it for my matrix Y so that they are in the same coordinate system. Now, this should be UR, and then times the matrix Y. Now, the general principle here is, if you think about POD, what's happening is you are just projecting onto the first R POD modes. Now, of course, POD modes, or the SVD, organizes those POD modes in terms of importance. That's because you have the singular values ordered from highest to smallest, right? So effectively what this is doing is reducing you by projecting you onto just the most important nodes. And of course, R is going to be user defined. I'm going to show you an example in a moment here. But this hope here is that you've simplified the problem. And in fact, what I'm going to show you is that as you delay more and more here, you can get very, very complicated POD modes, but the time dynamics inside of these things become increasingly simplified. And what happens when you implement this sort of method by reducing the rank first, you actually shift the complexity in time to the complexity in space. And that shift is coming from projecting onto these modes to become increasingly complicated. But the result is the time dynamics contained inside of these matrices become increasingly simple. In fact, they become linear. They become sines and cosines. Now, this will become a little bit more apparent as we learn more about the Koopman operator in the next lecture. But first, let's just do some numerical exploration based on these sort of two approaches, and let's see what we can find first. All right, let's take a look at an example. Let's start from where we started with a very, very simple sinusoidal signal, okay? So here's my MATLAB code up on the screen for you. And you can see what I'm doing here is basically choosing the number, this num_osc parameter. This is the number of oscillators I'm going to include, the number of sines and cosines effectively. And I'm really going to sort of randomize this in the sense that my frequency of my sines and cosines I'll use will be a number between 0 and 20, right? So sine of 19x or cos of 12x or t, whatever it happens to be. And then I also randomize whether or not it's going to be a sine or a cosine, right? So just a sort of binary choice. But this is really just to kind of make the signal very, very random. And then I'm going to choose coefficients in front of that signal from the uniform distribution from -5 to 5. Really sort of mix things up a little bit. And then we know from the theory that was just told to us is that the number of delays that one needs to use here is going to be 2 times. So the 2 comes from the fact that we have, sines and cosines, they double up in the complex Fourier domain, right? So e to the minus t and e to the plus t. And then the tau that we're going to be using is the delays -1. We'll create the Hankel matrix, and then we'll create this autoregressive moving average model here. So let's take a look. Let's see what we can find. Here we go. Here is our signal that we can see in the background in blue here. And then superimposed over in top in the red is our reconstruction of the signal. Now you can see that this is a near perfect reconstruction. It's really sort of hitting this exactly, and that comes from the theory that was spelled out in lecture, right? You just need to have enough delays in order to exactly reconstruct these things. And you can do this in a more complex way. You can add a whole bunch more oscillators here. So let's do it with 8, for example. Let's run this. And now you can see a really, really what would look like a very complicated signal. You can see it doesn't look like there's any sines or cosines, any signatures of simplicity in here. But because this is itself a band-limited signal, if it has only finitely many coefficients in the Fourier domain, you can perfectly reconstruct it with enough delays. Okay, that I cannot emphasize that enough. If there's not enough delays, then it will not be able to reconstruct, as we saw with this explicit example given in class in this lecture. Now let's do another example where we're going to generate a signal from the van der Pol oscillator. So the van der Pol oscillator is a very, very famous dynamical system that generates what are called relaxation oscillations. These are very sharp and singular oscillations. Here I'm showing you the signal x of t and then also its derivative. Now essentially what you can see with the signal here is that it's a very, very sharp decrease, and then what feels like a slow incline, and then a sharp increase, and then a slow, sharp, right? And this is really pronounced in the derivative down here, where you see these massive spikes around these transitions that you have, but then relatively nothing in between. Now, this is a genuinely extremely nonlinear oscillation. We know that it's not composed of finitely many Fourier modes. And so there is no number of time delays that's going to be able to fully reconstruct this signal for all time. It's a nonlinear oscillation. So what we could do is we could play around. We could say, well, what happens if I only use, let's say, 10 delays to build my Hankel matrix? How good will this reconstruction be, my DMD reconstruction? So this is in blue dotted up here is the original van der Pol signal. In red is my DMD prediction starting from exactly the same point. You can see that this is junk, right? The only thing that it does is maybe gets maybe the first time step, okay? And that's about it. So clearly we need a few more delays. The nice thing about this method is it's not expensive. You can just increase these delays. You can see how quickly this is running. Now I have 100 delays. Okay, that's a little bit better. It pushed me a little bit further, right? I got up to about 5 time points here. That's pretty good, right, so far, but I think that we can do better. Again, it's fast, it's cheap. I can just keep cranking up the delays. Let's go to 1,000. Here, look at it, didn't take much time to run, and I'm just using a standard, MacBook here, nothing fancy. But now take a look at this. Our reconstruction, our DMD reconstruction is pretty darn good, right? You can see that it's following up until maybe around 70 here, where you can notice, some blemishes starting to form. And again, I want to remind you, this is a genuinely nonlinear signal, and I could never reconstruct it with, a finite number of delays. I can keep increasing the delays, and this will look better and better, but only for finite time. Eventually, this is going to become inaccurate. However, that's pretty darn good with 1,000 delays. You saw how fast it runs, and look at that reconstruction. That's pretty darn good for a very complicated signal. Now, I want to keep playing with this signal, and what I want to do is I want to use the other method, the SVD-based method, the POD method, where I do these low rank reconstructions. And the first thing I'm going to do is I'm going to take that Hankel matrix, capital X, if you remember, and I'm going to apply the SVD to it, right? So here I'm going to use 100 delays, so that's tau is equal to 100. Create the Hankel matrix, apply the SVD. So this will take a moment because the SVD is relatively slow. But here's what we have. So let's explain what's on the board. Here what I'm plotting is the energy of the singular values. You might recall this from the POD lecture. It's just the square of each singular value divided by the sum. So you can see that there's basically one singular value way up here that's like over 50% of the energy. And down here, maybe there's one more. It's about 20%, as you can see on the screen. And then most of the other singular values are around 0. So there's only sort of 2 singular values or 2 modes that are doing all the work here. However, what I've plotted now is the time signals. So remember, I did this x sub r, which is whenever you project onto the time dynamics, the orthogonal modes. Here's the time dynamics. And again, what you can see is these are the time dynamics of the first 4 POD modes. Effectively, these are very, very complicated oscillations still, right? I had told you, or I had prefaced, that this should make things relatively easier, but these are still very nonlinear oscillations. If you take a look at them, they're jumping around, they're very flat, they have these sort of multiple timescales going on. And so I'm not sure that we made our lives any easier, because we could apply delay DMD to these, but would it actually help? But bear with me, okay? Just bear with me for a second. Let's crank up the delays here for a second, and let's see if we can do better. Okay, so here you can see that I cranked up the delays to 1,000, and take a look at that now. Now, I would argue that's pretty darn good. Take a look at what's happening here. There are two singular values that are very close together. They're about, one's about 0.45, so about 45% of the energy. The other one's about 0.4. And then there's another pair down here. Now, the time dynamics that are associated to these, the two up top, are these ones in the middle panel here. That looks like sines and cosines to me, right? Similarly, the next two on this little plateau also look like sines and cosines. Now remember, this is from the original van der Pol signal, right? We had a very complicated nonlinear relaxation oscillation here. But what the time delays did through the SVD is they took what were really complicated time dynamics through the delay, shifted that to the sort of space, the POD modes, and what you're left with in time is very simple oscillations. Now that means that by doing this projection with the SVD onto this capital XR and capital YR, I could now apply delay DMD to these, or I could just apply regular DMD to these sine and cosine modes. I can reconstruct these things all day. It is not a coincidence that they come in pairs, right? They come in pairs because you could think about these as sine and cosine, or you could think about them as, e to the ix and e to the minus ix, for example, or t, pardon me. So for example, let's do this. Let's take these first four modes, which together I've calculated constitute 94% of the energy. I'm going to set my R value, my target rank, to include 94% of the energy, and I'm going to apply DMD to these four signals. Now, remember, when it comes to DMD, what we care about is the eigenvalues of the DMD matrix. They give us the expansion. Here's the eigenvalues. There's four of them because it's a four-dimensional signal, right? V1, V2, V3, V4. They both look like they were sines and cosines, or at least some mixture of them. And here you can see the DMD eigenvalues, all four of them, from a 4x4 matrix, come in complex pairs, and they lie on the imaginary axis. This is no coincidence, right? Because eigenvalues on the imaginary axis give me rotations. That means that these things, that these projections onto these POD modes are in fact sines and cosines. They do not, they don't just happen to look like sines and cosines. DMD tells me that they are sines and cosines. I can reconstruct this signal perfectly. And remember, both of what we've seen today is based on this Hankel matrix construction. By delaying the coordinates in such a way that you inflate the spatial dimension, you transfer the complexity in time into the complexity in space. And that's something that DMD can handle very well, right? DMD gives you really complex spatial modes, the DMD modes, the eigenvectors, but it gives you very simple time dynamics, sines and cosines. That is the theme of what we've seen today, and here you can see it works beautifully. All you need to do is crank up the number of delays. This is an external hyperparameter that you can change. You've seen it here with my simulations. It's quick, it's efficient, it's easy. If you want to forecast really complicated signals, you can do it so easily with this method. Now, as I alluded to, there is a strong connection between what we saw right here with these time delay coordinates and this sort of POD method on the Hankel matrix and what's called the Koopman operator. So in the next video, we're going to come back, we're going to introduce the Koopman operator properly, and we're going to talk about how we can approximate it and how we can inflate the dimension of these signals in a similar way to delay DMD. So I'll see you all in the next video, everybody.